podium source.
Thank you so much for inviting me. This is a pleasure. It's a pleasure I hope to get to chat a great deal with all of you here for the workshop together. My name's Alex. I work, Sandia National Labs is a big place, but I work in this tiny little bit of it that is a science user facility. So just like maybe some of your colleagues apply for time on telescopes to image the stars, you can apply for time to work with people at SINT. There are 5 of these. So look like the light sources, maybe the photon source, and anyway. My talk today, I'm a physicist. My talk today is on classifying material topology in real space using homotopy. The image you should have in your mind as I'm describing all of these techniques is of a mathematical SEM. So we're going to drag around some probe in space and energy, and in doing so, we'll map out the local topology the entire way through. And that will provide us a much different way of calculating things than you would get at fan theory. I right up front want to acknowledge all the people that I've had the pleasure of working with on this. I'll be showing a lot of work today from Stefan, who just left my group to do a second postdoc at CNRS. And there will be a couple of results from Keon. You'll notice a bunch of the faces here in the room, and then people who funded this. Big picture, it's this operator-based approach to topological physics, and it's going to use this framework. I think that Emil was maybe briefly mentioned of the spectral localizer. It certainly came up with questions. There are going to be a bunch of aspects of this that are provided that maybe band theory can't access. So how you can get topology in systems that don't have a bulk spectral gap. And I'll explain both why that's super useful in realistic settings. Then I'm going to go through a bunch of different examples of how this framework can be applied beyond just Chern numbers. So crystalline topology, dimensional reduction in a topological superconductor into I'll talk about the quantum spin Hall effect. I don't want you to get the impression, I'll start with Chern numbers. I don't want you to get the impression that this is only good for Chern numbers in 2D. It works in the whole Cerjan table. I just want to show results from all of them. I'm a physicist, so I need to justify my stuff in terms of widgets. Why would we want to make a topological widget? So there are a few different answers. The first is a topological field effect transistor. These were kind of originally discussed in 2014. The idea is that you use the dissipationless transport, something like a quantum spin Hall effect, and its spin edge currents. Because it's dissipationless, it's a more energy efficient system, and so you could potentially build a transistor that is cheaper on your computer's power source. Low power topological magnetic memory devices. Again, this is a power argument, so that you can make memory that's again cheaper on your computer's power source. This is a big deal, right? If you're talking about a data center. So then the final is fault tolerant quantum computation. I'm sure this is the example maybe most people are familiar with braiding with Hemmingwells and superconductor. My background is in photonics, so there are some reasons why you want the photonic analogs of these electronic effects. The first is in building a on-chip laser. So what you're seeing here, this is a picture, but what it's imaging of is a photonic Chern insulator made out of a photonic crystal slab. So this would be some laser on chip that then would produce light coming out the side, and that you would route throughout the chip. And the reason you need this is that anytime you build a laser, the gain action inside of a laser, the nonlinearity that lets it laze, is typically very sensitive to external perturbation. So whenever you build a laser, you have to put an isolator after it. And the isolator protects the gain medium in the laser so that light only comes out, doesn't come back in, and it doesn't disrupt the lasing action. And if you could build then a laser that has a built-in isolation mechanism, you are reducing a whole component. And it's actually really important because the isolator that you use technologically is called Faraday rotator, and it requires hitting a big magnet on top. It's just big, not big, it's, a little neodymium rare earth magnet that you sit on top, but big relative to something that you want to stick on a chip. That's big. And so all of these things is just in the device community, you would lump this together and call size, weight, and power. It's acronyms to swap. But it's a way of improving on these characteristics that you would need to then build a device. Because you want to put these things in satellites, you want to put them on aircraft. That's anytime you can reduce a whole component or make a component smaller, it's a big deal. So we built lots of those. So if you had a photonic equivalent to a Chern insulator, you could build a laser, and it's been realized a couple of times experimentally, though those realizations aren't yet ready to go with satellite. But if you could make a robust photonic Chern insulator, it'd be very easy to then sell that to all sorts of people. The routing of quantum information. So this is using the photonic equivalence of the quantum spin Hall effect, Valley Hall effect. They route circularly polarized light to different output channels, and even in a single photon regime. And then creating cavities. So this is crystalline topology, higher order topology. And here the idea is to create these kinds of corner states. You could then imagine sitting color center or lasing on these zero-dimensional defect states that are there, and that is a useful way of controlling quantum information in, say, a color center state, or creating lasers. I'll show lasers and make with these in the slide or two. But all of it's about creating, states that you can control the propagation of with a useful technological application. This is a more modern perspective. I think Vladimir will be talking a great deal more about this in his talk tomorrow. But the idea is, rather than thinking about the edge effects of topology and why does use the utilization of bulk boundary correspondence to give me something on the boundary that then I can use as a widget. Here, topology is a route to delocalization in the bulk. So how do I make use of the delocalized states that exist inside of my bulk to, again, realize odd phases? So this kind of delocalization is a path to correlated phases in electronic materials. So rather than, again, focusing on the edge state, I get an Chern insulator. Chernness makes my bulk states delocalized. And so when I cool the temperature down and increase the strength of my interactions, these overlapping electrons then are more likely to exhibit correlated phases. So, and the same thing is true, we suspect, in photonics. Again, if I delocalize in a single particle wave functions, they are less going to be average out over fabrication disorder in my sample. And so it'll be much easier to create things like large area single mode phasors. Again, physicist, but that's the point, is that you have these bulk states, and topology is forcing you, even if you don't have great edge states, so say something like fragile topology, where you're not guaranteed a bulk boundary correspondence, it still guarantees these delocalized bulk states that then can herald other useful phenomena. So we have band theory that will let us find topology and materials. We have all these applications of materials. Why is this not a solved problem? Do we still study this? I don't think I need to say this for this audience, especially after Emil's talk, but of course, where you can apply band theory, you should. And but there are lots of cases where band theory is not useful. So you might lack translational symmetry, as Emil was showing, with quasi-crystals and amorphous materials disorder. I want to add to that finite size effects. So how close is too close for when I'm going to gap out two edge states that are nearby. You could have a heterostructure that lacks a complete or incomplete band gap. So band theory is applicable, but there's no rigorous definition of topological protection, because any arbitrary perturbation would potentially shift what states are contributing. Or the system is nonlinear, and for now I'm going to mean this in just like the classical mean field limit. But you could imagine taking this to many body systems. I'd be happy to talk offline about that with people later. I want to put a pin in this. Emil was talking about Amorphous materials and quasicrystals. Again, I'm a physicist. I'm going to talk about widgets. There was an enormous survey done in 2019 of basically every crystalline material that was known is known in standard databases. These are materials that someone has carefully gone through and done density functional theory calculations of, mapped out their band structures, talk all of this in a giant table. And the paper concludes, so they survey these nearly 40,000 materials. They find about 8,000 topological materials, at least with respect to some classification in the AZ table. But if you read the conclusion and then say the newly found materials are not substantially better, so these are all crystals.
You just have an error from quasi.
Well, okay, sorry. This is just like fine. All right, graphic designer Terry. So the point being that while there are many fewer DFT simulations that are known of quasicrystals, it's a much harder problem. As you truncate the large unit cells, you can't always use the plane wave expansion basis that DFT codes work in. If you want to realize, like, what this is saying is that we guessed at kind of the best topological materials, electron topological materials in our 2015, and we've never found anything really substantially better than them since. They're not, people have been trying to make those materials into widgets for a decade now. If you want to do better, you need to look where these other theories didn't apply, so that they are not included in these kinds of searches and you couldn't guess at them. And there are good reasons to look here. There are lots of quasicrystals that can contain heavy elements that are associated with strong spin-orbital coupling. So it's I think there's a lot of reason to revisit this class of materials. All right. Challenges and invariance in gapless systems. One of the first demonstrations of the quantum Hall effect, they did measurements in antimaty in addition to a gapped material. And what's interesting about their measurements in antimaty is they do see these the edge states associated with quantum Hall, but the system isn't gapless. And so they point this out in the original observation paper in 2009. And the point being that even though there's an incomplete band gap that spans the whole Brillouin zone, you really decide where you want to, say, define your projector and calculate your Foucault-Mealy index for this system. Problem is that anytime you start to add disorder to this, you of course collapse the Brillouin zone, and you no longer have an incomplete band gap where it's well defined. So even though you see them in the experiment, what is your rigorous definition of topological protection material? This problem occurs all the time in photonics. So we see each other. Photonics for light, air is metal in that sense. It conducts photons. And so air is generally gapless for light. So anytime you're building something like a photonic topological insulator, even if the object itself is an insulator, it's the heterostructure of the material plus the surrounding air that it's embedded in. Because your system's basically always truncated in air. It's always going to be a gapless system. The problem is even worse in some of these materials. It's very difficult to break time reversal symmetry in telecom frequencies. And so you'll find these systems that have very small band gaps in them. So this is using a material called ytterbium iron garnet, YIG, which is the best material we know of for creating something like a photonic churn insulator. It gives you basically a vanishing band gap for these designs. So it would be really useful if we could rigorously say, can we both classify topological phenomena and talk about its protection in the absence of a spectral cap. This would give us something like a chiral edge resonance. So you wouldn't be guaranteed quantized conductivity, but a state for making a laser, we're talking about 10 to the 10 photons. If I lose 2 of them to the bulk, I don't care. There's gain. It's a non-Hermitian system. So a resonance is good enough for this. Twisted systems can easily become quasicrystals. They also have all sorts of domains in them. So this is some mapping of different domains in stacked bilayer materials. And you can see that all sorts of different, these are always heterostructured materials. The same problem is true in photonics. You can make arbitrary twist angles in these systems. So we really want a local measure of topology for rotation angles, even when they produce commensurate twists. No current theory for finite systems. So if you want to make a laser, you have, say, these corner states. How close can you drag the corners together and talk about these lasers being coupled while still preserving their topology? Or talk about, say, two chiral edge states to make a laser. I'm going to take one more second to talk about why. Let's say I'm building a laser. I have some gain medium that fills a 2D area. And if I then make a boundary of a heterostructure, my lasing light's going to go around the boundary. And it's only going to see the gain available at some little patch around the boundary. So all of the energy I dump into the bulk of the material here goes unutilized. This is a problem because the middle is going to catch fire. Right? It's an efficiency issue, right? I have a 1D path of my laser or a 2D amount of energy I pumped into my system. This is bad. Engineers do not like. What you'd like to do is instead draw something that looks like your old cell phone game of Snake. Right? Because now I have some dense packing that I can infill this material with. But now you need to really be able to answer the question, how close can I drag these two edge states before they couple and gap and they're no longer protected? I really need a local measure of protection to talk about something like this. How close is too close is a crucial question if you want to actually make these things real.
Otherwise, you'll get a bunch of little lasers isolated.
Exactly. And you'll have backwards propagating those. Still couple. Yeah, you lose everything you want. So yeah, so this really presses us into saying, I need a local measure of protection. Can I talk about protection here versus what's happening? In photonics, again, people are already working with these mean field nonlinearities. So these are both solitons in theory and then realized in experiment, as well as on waveguide array rings. So a couple of different platforms. But these solitons are living on just a few sites. These things have no bulk. You want to be able to talk about the topological phenomena or how they're connected to topological phenomena. But the excitation is living on 3 or 4 sites. What do you even mean when you talk about a topological invariant or that's protecting something like these finite solitons? So can you define an invariant without bulk? So again, for this audience, this probably doesn't need to be said. The traditional route, we have different crystal materials. We talk about their infinite, take an infinite variance of them, calculate the band structures. The band structures give us some variance. Of course, band structures are just a Fourier transform. It has to be possible to go straight from structure to invariant. Looking at this, Fourier transforms don't have a subtract information, just scramble it. So everything that I need to find invariance has to be in the materials themselves. As Emil was saying and introduced us to, there are a variety of known ways, at least for Chern numbers, to calculate real space invariance. Vitaly introduced one. Yanko and Rasta had a seminal paper 5 years later. The challenge from my perspective is that they rely on projectors, and projectors are difficult to calculate for real systems. Either your computer struggles, or you tell your postdoc or grad student to implement KPM, and they struggle. So someone and somewhere is struggling. More, maybe crucially, neither framework comes equipped with a local measure of protection. Once you talk about projectors, you've already assumed that there's a spectral gap. And so they're never going to let us get at a question. So there's a more modern flavor of topology or topological classification that starts with the idea of a Wannier basis. So rather than talking about band invariance, I take a Fourier transform of my block eigenstates of a single band, and this lets us describe localized Wannier functions that live on single sites. And so these are, of course, not eigenfunctions of your Hamiltonian, but if you want to think about electrons as marbles, this is what you should be thinking about. And the reason that this is useful is it lets us invert the understanding of topology. So rather than saying systems with a non-trivial Chern number do not possess a complete localized Wannier basis, so if I have this non-zero Chern number and I try and find all those maximum localized Wannier functions, I'll just be missing some. My basis is incomplete. It turns out that this is an if and only if statement. I have a bag of materials and I start pulling out materials and I find the localized Wannier functions and I find that I don't have a complete basis. It guarantees a non-zero Chern number. And that this is a generalizable statement to basically every flavor of topology. So things even like the quantum spin Hall effect, the statement then changes to incorporate the relevant symmetry. If I pull out my favorite materials from my bag of materials and I find I can't find a Wannier basis that also obeys Fermionic time reversal, I then am guaranteed a non-trivial quantum spin Hall invariant. This observation gives rise to Andrei Bernovig and his co-authors development of topological quantum chemistry, this reframing of find Wannier centers, then talk about invariance. Lets us is this idea that they use of you're talking, you have an initial material, you're asking, can I chop it up into an atomic limit, i.e., can I chop it up into some system where I'm guaranteed to have this localized Wannier basis that respects all material symmetries? And if I can continue my initial system to this atomic limit while keeping all my band gaps open and preserving all my symmetries, then I'm always trivial. If I can't, topological. They do this by enumerating every possible atomic limit for all 230 space groups, or now all 1,400 and something magnetic space groups. So there's some giant table of every single atomic limit possible in these different settings. And they're asking them, based on the bands of a known material, is it compatible with the summation of these atomic limits? But this observation of taking a material and dividing it into and looking for these localized orbitals in momentum space gives rise to an analogous statement you could make in real space. So you're asking, can I start with some Hamiltonian of my system and say some position operator that labels all my sites? And can I path continue this to an atomic limit where I have a bunch of isolated disconnected molecules? So my Hamiltonian and the atomic limit is block diagonal, which is just each block representing each molecule that I've kind of smushed together. And crucially, each site now within this has the same position. I've kind of taken separate things and thrown them infinitely far apart, and I've taken things that were similar and smushed them together. So in an atomic limit, my Hamiltonian commutes with my position operators in arbitrary dimension. So I started with non-commuting matrices. My atomic limits all have commuting matrices, and so the equivalent statement is now asking in real space, can I continue my initial lattice to my atomic limit, while again preserving all my symmetries? That's an easy thing to see how I do that along this path, but preserving my band gap. I will elaborate on that in a couple slides. But that's the name of the game of this real space classification. And to do this now, this is a question about matrix homotopy. Right, non-commuting matrices, can they be path continued to commuting while preserving some salient set of properties? That's a matrix homotopy question. To do this, there are going to be two theorems we'll use in the Chern case. The first is that two invertible Hermitian matrices, L and L prime, can be connected by a path of invertible Hermitians, if and only if they have the same signature, difference in the number of positive minus negative eigenvalues. This is easy enough to visualize. These can be path connected without having an eigenvalue cross through 0, where it would be non-Hermitian or a non-invertible. These have a different signature regardless of how you do your matching. They'll always have to, their path will always become non-invertible somewhere in the middle. The second theorem is a much more modern one, goes to Choi in 1988. If you have two Hermitians that commute, R and S, the signature of this funny looking thing is guaranteed to be 0. If you plug the physics back into this, yeah, I know, right? Fact. But if we plug the physics back into this funny looking thing, let's let R be our Hamiltonian, centered at our, with 0 chosen to be at our favorite choice of energy. So this would be the Fermi energy. Let's let S be our position operators centered at our favorite choices in location, little x, little y. This requirement that they commute now becomes a statement about H and commuting with x and y. And so what this is telling us in this, once we stuff the physics back in, is it's telling us that atomic limits have signatures 0. Atomic limits have commuting Hamiltonian with position. Plugging this back in, I get atomic limits have signatures 0. I can call this matrix, when I plug these things back into this definition, the spectral localizer in 2D. And so now the statement is, because I know that invertible Hermitians can be path connected if they have the same signature, this is a statement that, okay, even if I don't have commuting H, X, and Y to start off with, if I go around looking for my favorite choices of E, X, and Y in my material, and I start scanning this tip around, anytime I find a signature of 0, I'm in a trivial limit. And if I ever find non-zero signatures, then I know I have something topological going on. Intuitively, again, physicist, so I'm going to think on the back of the envelope. What we've done, if you squint at the formula from the prior slide, is taken these three pieces, 3 operators that contain orthogonal information, and I've tensored them against some matrix elements, the polys or Clifford representation that somehow preserves that orthogonality while letting me smush them together into a single matrix. And so it's somehow preserving this independent information they carry while letting me form a single matrix that conveys all of this. And this comes automatically equipped with a local measure of topological protection. I cannot change the signature of my matrix without one of my eigenvalues of my Hermitian matrix first going to 0. And it's Hermitian, so it can move, all my eigenvalues can move most at linear speed. And so the minimum eigenvalue, the eigenvalue of this localizer closest to 0, is by the definition a measure of topological protection. It's always going to move continuously. It has to cross 0 from some perturbation. So I know that any perturbation that's norm is not big enough can't change my topology. So it's a quantifiable measure of protection. What does this look like? If I have, say, a Chern material inside a trivial material, I can calculate its local density of states and the mutual band gap. I find the chiral edge states running around the boundary. If I calculate this local gap mu from the last slide, I see that it closes around the 2 materials. And inside I find a topological index, and outside I find a trivial index. So this whole picture is consistent. It even has built-in bulk boundary correspondence. So anytime that you find that this gap is close to 0, this local gap is close to 0, you're guaranteed that there's a nearby approximate state localized there in both position and energy. And so local crossings, that closing is guaranteed nearby states. This is Freddie and Terry's result from a couple of years ago. I also started off by saying I didn't want to calculate projectors. And then I told you I needed to find a signature, and that the signature is the number of positive eigenvalues minus the number of negative eigenvalues. That seems to have not solved my problem. Fully diagonalizing a matrix is an expensive endeavor. The point is that there are some terrible, I think probably many people in the audience appreciate, there are terrible things you could do to your matrix that do not preserve its spectrum, but do preserve the signature. And so to calculate a signature of the number of positive eigenvalues minus the number of negative ones. I need to know 0 actual eigenvalues. I can instead do something like LVLT. And even though D, N, I'm not trying to not overload L. N is a lower triangular matrix, and D is diagonal. D is not the spectrum of L, but signature is the same. And this is much faster to calculate. So we can use this in gapless systems. So this is a metallized Haldane model. This kind of model was originally introduced by Bergman and Gil Raphael in 2010 as a way of trying to explain these results in antimaty that I showed in the introduction. And it's a Haldane model, the honeycomb here with an interstitially placed triangular lattice that's all coupled together. So 3 sites per unit cell, a 3-band model. We can tune that third band to sit right in the middle of my Haldane band gap. And you can, if you look at, say, the ribbon band structure of your system, you can tune it to have things, chiral edge states or not. So you would say that the red one is the topological case and the blue one is not. But if you set your Fermi energy right at 0, there's a bunch of bulk states. Their local density of states, if you just go about calculating this, are not qualitatively different. It's just states everywhere, as you would expect. So as I said, this was studied by Bergman and Raphael. They found boundary localized states that were resistant to hybridization and robust against mild disorder. That's about as far as they could push their study because they didn't have a way of classifying it. It's a gapless system, all sorts of bulk states. And there's, at the time, there was no measure of local protection for this. We can do this with the localizer. So even though their LDOSes look the same, if you spatially map out that local gap quantity mu, that smallest eigenvalue of the localizer, you can see that it has to close all the way around the boundary of the system that's topological, even at energies in the middle of the gap, because the topology is changing. And if you look at the trivial system, you do not see this closing along that boundary. So you can immediately look at this plot of mu and say, this is topological. And you can calculate the index. You see that the signature changes. Maybe the big point is that even though H at the Fermi energy has eigenvalues at 0, the localizer can still be gapped at that same energy. And so your protection is weak. Again, this will not give you quantized conductivity. I'm not saying that you're going to still get quantized conductivity here, but you're guaranteed one of these chiral edge resistances. You can do this in a disordered system, identify local gaps, classify local topology. You can find, say, islands that turn on disorder where topology has changed. You can do this in an experiment. So this is artificial graphene. This is a heterostructure made of a quantum well material. So there's something like 20 or 30 nanometers thick of a quantum well with 2 barrier materials on either side. You then etch holes into it. The etched regions are where the electrons do not want to live. It's a higher potential. So it looks like a triangular lattice in real space, but what the electrons see is a honeycomb lattice because the electrons don't want to live on these holes. So it forms a honeycomb lattice of with atomic sites that look like these blue dots. This is pretty standard semiconductor physics. These are effectively non-interacting material electrons. Their kinetic energy is too large for their Coulomb interaction to really matter. Another experimental detail is that the Fermi energy tends to be much higher than the background potential. This is a problem of either you need to make the pattern much smaller, or you need to reduce your carrier density. Both are hard problems. Nevertheless, you can make this thing. You can map out its the longitudinal and transverse resistivity. So you can see the quantum Hall effect. So because the Fermi energy is so much higher than the background potential, kind of zooming out, you just see the quantum Hall effect. The key point is that if you look in between your Landau levels, you see a non-vanishing longitudinal resistivity. This is real. This is due to states that are disordered and percolating states that appear that are wrapped around each of these holes. I'll show you more about them on the next slide, but these have been seen. We can reproduce this in simulation. So you can fit the parameters of this equation to the lambda level. So you're just matching the local density of states to the longitudinal resistivity. We can again see, adding in disorder, that there is a non-vanishing density of states between the lambda levels. And nevertheless, using the spectral localizer, we can map out exactly the quantum Hall plateaus in this gapless experimental system and find essentially perfect. Again, I want to emphasize this is not a tight binding lattice. This is not a low energy approximation. The matrices that are being stored in memory here are enormous, 10 to the 6, 10 to the 7 squared. But because we can use sparse methods, it's not a problem. We can do these on a modest workstation or even a decent laptop.
Why do you say it's gapless? Because having the magnetic field.
It's gapless. Yeah, there are these pin states that are. What do the pin states look like? Yeah, so the pin states look like this. They are bound kind of to each little pillar. And they have been observed. You can find papers from 91. I think the first paper on them was from paper was 91. Yeah. So what you get here, so one of the things the localizer comes equipped with, I talked about this, briefly talked about this parameter kappa, that's fixing units. I want this whole thing to have units of energy, so kappa has to have units of energy divided by weight. You can, if you want to probe system level phenomena, you can talk about the bulk gap of your system, if there, something like a bulk gap divided by the length of your whole finite weight. But if you want to probe topology on a more local scale, you can reduce that length to say be the antidot. We call these pillars that have been etched in, called antidots in literature. The diameter of these pillars of the potential. And so you're treating, what this is effectively doing is treating spectral resolution. So I'm going to have much more uncertainty in the topology I can identify energy, but I have much greater spatial resolution. So I can only do this at locations where I have a larger gap or effective gap, say for the higher, the lambda levels at higher field. And so if I look at this, we'll look at now the ordered system with just one spin component. I can look at the background topology that I was plotting on the last slide, the flake level topology that's shown here in red. This is the index. And I can then look at the topology associated with this different kappa that's going to probe what's happening on these antidots, shown here in the dashed line. And you can see that these are moving at different times. And so you can, for example, look at when I have a shift in my background topology. This at a flake level, this should correspond to a lambda level. And so if we look at the density of states of this lambda, this large peak in my density of states here in blue, I see an extended lambda level across my whole sample, exactly what I would expect. I can do the same thing for when my topological index on my antidots is shifting, that dashed line. And I can see states, bulk states that are living on every single antidot in my system that are extended across the sample. So the claim is that these shifts are lambda levels, that this set of pinned states to my antidots represent a lambda level in my system. I can look at when the two indices are the same. I can just see my LDOS just reveals states on the boundaries of my system. These would be flake level edge states. And if I look at these other oscillations now in my density of states when the two trim numbers are different, what I see are these ring states that live around each antidot. And so what the claim here is, and that these simulations are showing, is that these states that were previously known to exist that were pinned to each antidot are actually of topological origin. They originate from the difference in local topology of what the Chern number on the antidot is versus the Chern number in the background.
Sorry, Alex, what's your antidote? Are those the blue dots?
Well, the blue dots are the electrons, the antidots are the pairs.
Oh.
The process.
What's the quotient of two kappas? The order,
Is it 10 or is it
Yeah, 10 or probably 50.
50?
So I'm confused. In E, you're saying that the state lives on the antivals.
Yes,
You have states living on the pillars.
right.
Really around the points.
No. So remember, the Fermi energy is higher than the pillars. So I can have states that live on the pillars and just see something like a mismatch in potential that is confined. Right, and then I have states that live around the pillars that I would now say are chiral edge states of topological origin or chiral interface states. And you can even see these oscillations here, I suspect, are due to just the 2-pi periodicity that is discretizing the allowed states around each pillar. We can, again, because I do not need a low energy approximation in my system, I can talk now of, and I don't need to assume anything about gapless. I can talk about transitioning from a totally open system, gapless, unpatterned 2D, gapless unpatterned electron gas, all the way up to an infinite potential where you'd expect the Hofstadter butterfly limit to be exact. And everything in between. And so that's what you're seeing here. These are, of course, just simulations. But you're seeing the localizer now mapping out these different regions of intermediate potential strengths. You can now see the formation of Hofstadter's butterfly for these finite potentials without needing to play any games with unit cells. Kind of typical way you do this argument is expand your unit cell, try and drive your potential to zero that way. But we don't need to play any of these games because we don't need a low energy limit. This, as I was discussing earlier in photonics, we have this gapless material medium that surrounds every device. The original realization of topological photonic churn insulator is in microwaves. If you bound a microwave in metal, that really does approximate having an open boundary condition in the traditional condensed matter sense. And so they observe all of the expected condensed matter phenomena. Later realizations in, say, helical waveguides or ring resonators are surrounded by air and not a metal or not an open boundary condition. So these will have this exact problem I was discussing of light radiating through space. They will radiate. So these do not, I would argue, represent kind of classic example that we expect from condensed matter, where I have a gap material next to a gap material and some interface between them where I have states. They look like a trivial gapless material that's air next to a topological gap material. And so if our usual argument is that I need to unscramble some band inversion taking place in my topological material relative to my gap, my surrounding insulator material, well, there's no unscrambling that needs to happen when I have a gapless material. What is it? You know, this picture that we have of band inversion. It's not really clear what I need to do here, or if anything needs to unscramble at all. Of course, we know that these experiments work. I'm not trying to say that the experiments are wrong. I'm trying to say that we should have math that describes these experiments. We can take Maxwell's equations and turn them pretty quickly into to give us a Hamiltonian, an ordinary eigenvalue equation. So at finite frequency, we only need 2 of Maxwell's equations. We can easily convert them into a generalized eigenvalue problem, and then sure, you get an ordinary eigenvalue equation using kind of standard manipulations for dielectric materials. Will get us. This is very standard. And using this, then Hermann and his student Lars worked out that if I had we need to simulate free space, so I need to have radiated boundary conditions, non-Hermitian. And the correct modification, at least for 2D class A, that Hermann and Lars worked out was to add an adjoint to one of the matrices in the localizer. And this works. So we can take a 2D photonic crystal. This is, again, real Maxwell's equations, not a type binding approximation or anything else low energy. We can turn this into the Haldane and Ragu model, which is topological. We can open a gap. We can plot the LDOS of this kind of system. PML stands for perfectly matched layers. It's a radiated boundary condition, so light can be shut off to infinity in some rigorous way. And if you plot, say, the LDOS in the middle of your topological band gap, you see a chiral edge resonance, not a resonance because it's going into its bulk in the middle, it's not, but it's shedding energy like crazy out to the boundaries, like air, it's radiating. Nevertheless, we can use this reformulation of the spectral localizer to rigorously say that the domain in the middle that you would expect to be topological is. And we can see the eigenvalue of the localizer crossing zero, and it's locally changing the signature, and it's responsible for this classification. And assign protection on both sides. We talk about the protection of this chiral edge resonance, both the perturbations inside of our photonic crystal and the perturbations in the air in some meaningful way.
And 1 second.
Yeah.
What exactly is the localizer in this case? Do you use finite elements or do you use the actual? I mean, I guess you could formulate this a differential operator as well.
Yeah, so here we're using finite difference. Yeah, PMLs are pretty easy to implement. Finite difference. Plus I have code, so it's easier. We have done this. I won't show the slide because I didn't think anyone cared, but we have done this with FEM in 3D. You need to do something a little different than this in FEM. So moving on from Chern materials, we can talk about a local winding number. In 1D, you can pick your two. You have 3 poly matrices. You only need 2 of them because there's only 1 position operator. You can choose them so that the localizer is off block diagonal. Then the spectrum is duplicated across these 2 blocks essentially. And so we can work with one of these blocks. It's non-Hermitian, so we can use the system's chiral symmetry to restore hermeticity to the system. So we can talk about the symmetry reduced spectral localizer. I'm showing this just as a way of saying that signatures for, Chern numbers, I think as probably everyone in this room appreciates, Chern numbers are somehow like too obvious to ever be missed. You can find a Chern number in any number of different ways. The symmetry, the topological classifications that rely on symmetry of the material become a little more subtle. And this is an example of how we can introduce symmetry into the system, and that the localizer framework explicitly knows about this symmetry to make sure that we can restore any variant. None of these operations have changed the definition of the local protection. The smallest singular value of this matrix is the same as when we get all the way down here. It's a unitary transformation. But this way now it's Hermitian and can have a non-zero signature. This guy would have a 0 signature always. For a winding number, we expect an integer invariant. And this has been experimentally observed. So this was with Camila and Emil. Here are some of these printed resonators that Emil was referencing. And we can make a gapless kind of 1D chain by stapling something like an SSH model to something that is monatomic, make this gapless spectrum, and yet observe well localized states at the boundary at a domain wall between the 2. Even though the system is gapless, we can both observe them and talk about their topological protection in 1D. Because this is now just a statement of matrix homotopy and operator algebras, the physics can be abstracted away, and we can easily generate other invariants for different flavors of topology. So just as I was saying that we had a chiral symmetry that anti-commutes with the Hamiltonian, it commutes with the position operator, squares to 1, gave us a winding number. You can reverse this, talk about a spatial symmetry that commutes with the Hamiltonian, anti-commutes with your position operator, has the same other parameters, and so you could talk about a crystalline winding number for a system that can be dimensionally reduced to 1. So you can do this even, say, for a 2-dimensional system. Here's a photonic crystal, done again with finite difference. Yeah.
Sorry, Alex, so before we go further
Sure.
away from our question. So the original statement is that you want to see if you can smoothly deform your Hamiltonian into, or your system into something that commutes with the operators X and Y.
Right.
Right. So that's your criterion for calling something topological versus trivial.
Yes.
And the trivial are the obstructed atomic insulators because I always deform them into with the position operators. But now in 1D, I can always have a Wannier description of the band, right? So
yes.
these are all obstructive atomic
Absolutely.
insulator. So what's the role of how does the symmetry enter here now to make the statement of whether you can connect it to commuting or not commuting?
It's no, so it's always going to be commuting. It's just they're going to be different limits. So there are two the two obstructive atomic limits just can't be deformed to each other without closing the local gap.
Yeah, but in both cases, I can now make them commute with the position.
Absolutely. In 1D, in 1D, you're guaranteed that two matrices that are Hermitian can always be deformed to be commuting. So yes, no, it's the point is that these integers are distinguishing between different obstructive limits.
Right. So it's a finer distinction between what you previously called trivial.
Yes. Yes. Yeah, this one. Give me 1 second. I'll say more negative things about what we did here. I don't want to give people the impression that this is too good. I mean, it's good, but it's not. 1 second. So we can talk about. So this is again a full wave simulation of a 2D photonic crystal. We can plot its density of states because you have this boundary between two materials that are in these obstructive, mutually obstructive atomic limits. You can find that there's all sorts of states inside your global band gaps of the two materials due to both the edges and the corners. We want to find the ones that are specifically due to the corner. And so we can use an up-down reflection symmetry about just this axis here. That will let us define one of these crystalline local winding numbers or crystalline energy resolved winding numbers, and we can then plot this local gap mu based on this operator and see that it only closes at two locations inside the gap, where also the index changes. And if we pull out the local density of states of just the underlying crystal here, we see corner states. So this is a way of easily finding the corner states while ignoring all of the edge states. Now, just to make sure I emphasize this, this is an integer invariant. Vladimir, your prior theory would give CN invariance for this. And the point is that if I did this, say, with some exposed corner, I could always add states there. So it's picking up the fact that you can glue on extra sites, locally to the corner, and this invariant will pick those up. So that's where the integerness comes from versus this kind of. You can do dimensional reduction. So so I'm talking now about topological superconductors in class D. This is a Z2 index in 1D. Of course, this is a tire chain in 1D. In 2D, it's the Chern number. We'll take a model called the Shiva lattice, which are these imperfections on the background of a topological superconductor, on the background of a superconductor. This has a local 1D Z2 marker that's defined in terms of the sign of a determinant of the Hamiltonian and position operators. And what you can do with this is then just start with some disordered material, what's being shown here in the dark dots are the locations of these magnetic imperfections of white circles. So you can read this as a heterostructure boundary between two different materials. In this disordered circle, then we're going to look at the topology, just plotting this along the center axis here. You can then simultaneously look at both the 2D invariant and protection and the 1D invariant and protection. As we now change the distribution of these magnetic impurities from a disordered 2D disk to a disordered 1D line. And we can see then the transition from Chern topology to trivial Chern topology when the material basically becomes 1D, but the manifestation of robust 1D topology through this whole thing. So you can just directly, because we have this local invariant, we can just directly look at energy. We can just directly look at dimensional reduction by simultaneously probing both forms of topology as we do this material reconfiguration. I have 3 minutes left, so I want to briefly describe how we do classification for the quantum spin Hall effect. Again, emphasizing how we would put symmetries into this theory. For fermionic time reversal, you have Hamiltonians that can be written in this particular basis. In this basis, fermionic time reversal looks like this. And all of the system operators are even under this. So X and Y also kind of trivially satisfy the same form, and they're all going to commute with fermionic time reversal symmetry. So if you construct the localizer commutes with this flavor of fermionic time reversal symmetry when T has been tensored against the identity in the Pauli matrix space. The Clifford representation of the spectral localizer also has something like a time reversal symmetry. It would have some action just on the Pauli portion of the Hilbert space. And all of the Pauli matrices anti-commute with this operator. So the localizer also anti-commutes with this funny symmetry where you have the identity on your system Hilbert space and the Pauli time reversal symmetry in your Pauli space. What this means is that you can combine these two symmetries so that your 2D class A2 spectral localizer has a charge conjugation symmetry. So if we have charge conjugation that's the product of both, the localizer will anti-commute with this. And which means that there's a basis in which L can be both Hermitian and skew symmetric. So its transpose, where Q is this unitary, the basis rotation, its transpose will be equal to its minus. Because it's Hermitian and skew, it's purely imaginary in this basis. And this skew symmetry specifically lets us define, again, a different flavor of matrix homotopy that's going to let us get at the topological invariant. Just to give an intuitive example of this, the simplest skew symmetric matrix you can write down is skew symmetric, or is tridiagonal. So, and then it's all these little 2x2 blocks, where you have, say, some constant and it's negative on either diagonal. For skew symmetric matrices, you can define this operator the Pfaffian, which is going to be the product along one of these off-diagonal entries. It's going to skip every other element too. And this squared would give you this term. The key, though, as I think everyone appreciates, is that the Pfaffian has a well-defined sign. If we want to change the sign of our Pfaffian while preserving the skew symmetry of our system, what it's saying in this example is that I want to flip the sign on one of these blocks. And this is going to mean that I have to drag two eigenvalues across zero because they're going to come in pairs. And so this gap closing here is where my matrix homotopy argument would say I'm not invertible. So I'm preserving hermeticity, invertibility, and skew symmetry with this filter. And so this is now a question of, can I take these localizers in the correct basis or mute them into each other without crossing? And so that defines for us the C2 invariant, the sign of the Pfaffian. It again picks up the same local topological protection. We can test this in some quasi-crystalline system by, say, unifying Penrose tiling. And so we'll make, say, a topological flavor of this that has the quantum spin Hall effect on one side. We'll make the other side gapless just to show off. And you can see that our local invariant is going to exactly pick up the topological half. Our local gap will be large here, and our LDOS will show that there are plenty of states on the gapless side at zero. We can do this for really big systems. So we released code to do sparse signs of Pfaffian algorithms. So this is now it's in photonic crystal. It's a different parity-based invariant, but it's got really big matrices. So there's now public code for doing this. I'm going to skip through solitons. We can talk about topology without a gap. We can talk about if you say were to inject some light in here, it'll can drag with itself a local domain of topological no trivial later, which itself can talk about topological dynamics this way. And this has potential experimental utility for making reconfigurable topological structures. I want to conclude by just saying that this kind of brilliant brainchild of Terry and Hermans to write down this map is finding utility all across an expanding community in physics. The first paper using this in physics was Cosmo Folga, 2016, but then it basically just got dropped for 5 years. Why he chose not to continue with it at the time. But it's showing up now in a bunch of different theory papers. Locate topology, disordered topological superconductors. There's a nice proof of how the localizer invariants are the same as these other Kitaev and Resta markers now, based on physics intuition. There had been a math proof before from Terry. It can give you the non-Hermitian skin effect, at least in one-dimensional systems. And it's now showing up in a number of experiments. So just to conclude, as I've been describing this whole time, is some sort of topological SEM. We're going to probe the system with math, drag around this probe, find the topology of different conditions and figures. Terry and I wrote a tutorial on this with a physics bent to it about 2 years ago. But there's a section at the back that also talks about some of the key theory. Thank you.